What we see here are called simple hydrocarbons, compounds made up of carbon and hydrogen only. The simplest hydrocarbon is methane. It's also called a member of a class of compounds called alkanes. It's an alkane. And notice the ane suffix for alkanes. If we add another carbon and then round it out with its full complement of hydrogens so that each carbon has 4 bonds, we have ethane, propane, 3 carbons, and butane, 4 carbons. Notice for the middle carbon of propane and the 2 middle carbons of butane, they only have 2 hydrogens each. Because they're already connected to 2 other carbons, they have 4 bonds total. Molecular formula, something we are familiar with, of methane, for example, is CH4. So it's just a listing of the atoms. Ethane is C2H6, propane is C3H8, and butane is C4H10. Notice the molecular formula doesn't give much information about structure. That it's just a hydrocarbon is all you can tell. In fact, when we start adding carbon atoms and making larger molecules, we come immediately to the problem of isomers, or the concept of isomers, which are the same molecular formula different structure. In other words, the atoms are connected in different ways, in ways that would require you to break bonds and reattach them in different places in order to make the alternate structure. Now, we already did an example like this in video 1. This is another example, very similar, adding 1 more carbon and additional hydrogens. So, for example, best way to see this is to do a sample problem. Draw all the isomers of C6H14. So, the first way I would approach this is draw the full molecule out and make sure you know what you're working on. Carbon, carbon, carbon. There's going to be 6 of them. Carbon, carbon, carbon. Add the full complement of implied hydrogens. I'll get to that term soon. Such that each carbon has 4 bonds. And that should bring us to this hydrocarbon of C6H14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, notice how long it took me to draw that. We have an equivalent structure that's just a line structure. 1, 2, 3, 4, 5, 6. The line structure has a carbon on the end of the line and at each joint. 1, 2, 3, 4, 5, 6 carbons. These are the same. These are representations of the same molecule, C6H14. The carbons and hydrogens are all implied. What we call implied here. But notice how much more quickly you can draw this. And in fact, in most situations, I would say, it's better to have this sort of uncluttered view of the line structure. In a problem like this where you're trying to draw isomers, the first thing you're going to do is say, all right, if I disconnect a carbon on the end and put it somewhere else, for example, I can put it there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Just counting. This is a different molecule. It's connected in a different way. And in order to get from this molecule to the previous one, I would have to detach bonds, switch them, and reattach them. So that is an isomer, a structural isomer. With a molecular formula of C6H14, there are other structural isomers. And these are great problems because they reinforce bonding and structure a lot. They also reinforce other concepts like geometry, charge, and conformations that we're going to soon learn about. Another isomer of this has only a 4-carbon chain, for example. 1, 2, 3, 4, with carbons sticking out like that. That's clearly a very different looking molecule. Another isomer of this looks like this, and another isomer of this looks like this. So the way to really get good at this is to do these as practice problems. When we learn nomenclature or naming, another way to check your answer is to name each structure that you drew, because if they're different structures, they will end up having different names, and it's almost like a check. But it's pretty clear to see that all 5 of these are different molecules that would require detaching and switching groups of atoms or atoms. Now, a common mistake is if we look again at this top structure, what I see often is that someone will draw it like this and say that's a different one, just because it looks different. But that does not incorporate what we know about these molecules, and that is that they can rotate around any single bond. So there is free rotation around any of these bonds, including that one that I just indicated. All what we're seeing here on this structure is a rotation, and so this is the same as the first molecule shown. And therefore not an isomer, but it's a different conformation. Conformations are gained through rotation, twisting, flexing, if it's a ring, even bending, I suppose you could say. None of these actions require detaching and switching atoms or groups of atoms places to get from one structure to the other. To get from this structure to the one above only requires rotating around that bond. And if you build a model, it becomes extremely clear that that can take place. So that is not an isomer, but a conformation. Now, I mentioned naming earlier. So to name simple hydrocarbons, we have a list of the number of carbons and then the prefix that goes in front of what they are. So methane, interestingly, could be drawn just as a dot, actually. But methane, we know, looks like this. I'll just draw that out. The dot would be the 1 carbon. Methane is the suffix for alkanes. And so there's really no line structure version of methane. It's just methane. Ethane, you can draw ane in for all of those, has 2 carbons. I'll go ahead and draw it here with its hydrogens again one more time, but we're going to want to just skip ahead on this kind of thing. It would be drawn in a line structure as just a line, where there's a carbon here and here. That's ethane. Propane, two lines like that. Carbon, 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 3 carbons, 2 carbons, 1 carbon. Propane, propane. Butane, 1, 2, 3, 4 carbons. Butane, butane. Pentane, 5 carbons. 1, 2, 3, 4, 5. Pentane. Now, starting with butane, actually, you can have isomers. These are just the straight chain compounds, as we would call them. In order to just indicate that you are dealing with the straight chain, you can add the prefix letter N, that's a script N, as in normal. N equals normal. It actually does mean that. So N-butane and pentane, normal, quote unquote, is referring to what's normal, a straight chain. Remember, some of this goes back to the very first discoveries of molecules. Hexane or N-hexane. N-hexane. And the rest, it just keeps going in logical order. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Heptane. Same. Octane, nonane, decane. I'll let you fill these out on your own. When you get up to molecules like decane, you've got many isomers. So it's probably wise to say N or normal in front of all the straight chain molecules. So those are the simple hydrocarbons. Parent chains, when we do naming, I'm gonna call them parent chains. You'll see why. So here's an example of naming. What is the systematic name of this structure? And so the first task is to find the longest chain of carbons, find it, number it, and then decide on the substituents. And if there are multiple substituents, give them collectively the lowest set of numbers. So, perfect example of, oh yeah, I get it, I understand this, but until you do a lot of practice problems, it's not extremely clear. The longest chain is going to be 1, 2, 3, 4, 5, 6 carbons. So I picked an easy example to begin with. It's going to be the parent chain. And so we're basically starting with an N-hexane with a methyl group attached to it. That is a carbon there on the end in the line structure way of doing it. And that methyl group is at carbon 2 of the N-hexane. So it's 2-methyl N-hexane. Our goal with naming is to be able to have no ambiguity. And if you think about it, that's a major goal of all science, right? For a scientist to say, well, you know, it could be this or that, doesn't inspire a lot of confidence. So, no ambiguity. In other words, from this structure, there should be only one name generated. And if the name is correct, you should only be able to draw one structure from the name. That's no ambiguity. And practice will make perfect on that. I introduced already the name of this substituent. So a single carbon substituent with hydrogens on it is a methyl group. Notice the YL suffix, methyl. And so methyl, we've already seen. The way to draw it as a substituent is to say like a little squiggly line like that, CH3. So it's like methane, only it's a methyl group, substituent group. So this could be stuck on a chain of any of the parent chains above. An ethyl group is 2 carbons. And that's a lot quicker way to draw it than drawing out all the carbons and hydrogens. Carbon, carbon, ethyl group. Propyl group, I'll just write propyl, connected to something, anything, 1, 2, 3 carbons. But now there are isomers of these as well. So a propyl group could also be carbon, carbon, carbon. So in fact, we call this an N-propyl group and an isopropyl group. And it's kind of funny because it's almost as if they expected no more. Complicated. And so, because if there's, well, you'll see here with the butyl groups, you have more isomers. You have the straight chain version, 1, 2, 3, 4. N-butyl group. You have other versions. You have a branch there. 1, 2, 3, 4. Secondary or sec-butyl. You have 1, 2, 3, 4. Isobutyl. Notice how the nomenclature sort of loses consistency in times. Most nomenclature is a mixture of a systematic nomenclature and common names. And it's hard to overcome common names, especially if they've been used for 150 years. There's one more. 4 carbons. I'm putting these dots there, but that's not really standard practice. I'm just doing it to emphasize in this case. So tertiary butyl or tert-butyl. And then there's pentyls. There's all kinds of pentyls. Let's stay with these as what you're responsible for. The primary, secondary, and tertiary concept comes up over and over again in organic chemistry. What that refers to is that, for example, this carbon right here is a primary carbon because it's connected to only one other carbon. Primary carbon. Secondary carbon. Primary. Secondary. That carbon is connected to 2 other carbons. This is a secondary carbon as far as we know. We just don't know what's here, right? Notice the tert or tertiary butyl. This carbon is connected to 3 other carbons, so it's tertiary. As a substituent, it's tertiary. There is one other word that comes into play here sometimes, and that is if, for example, if there was a carbon here, that carbon that we called tertiary would actually be quaternary. But it's, I'm just going to throw that out there now, quaternary, and we're going to revisit this later at times. So here's some more examples. Now we know the approach. Find the parent chain, find the longest, most substituted parent chain. Longest chain, 1, 2, 3, 4, 5, 6, 7, 8. So it's an octane, N-octane. It has, so to number it and to give the substituents the lowest set of numbers, I would number it from left to right. But that is not always the case, and chemists don't necessarily always go left to right, right to left, up, down. We go in all different directions as need be, because we're dealing with really three-dimensional objects that can just rotate and flip around. We have 2 methyl groups at carbon 3 and an ethyl substituent at carbon 4. So the way that we would name this officially is 3,3-dimethyl 4-ethyl N-octane. And there is some redundancy here because we put the dimethyl to say that there's 2 methyls there, or anywhere actually. The 3,3 to indicate methyl, methyl, dimethyl at carbon 3. If one of these methyls was on carbon 6, it would be 3,6-dimethyl, for example. So that's the systematic name for that molecule. It's unambiguous. You can't draw other molecules with that same name. Longest parent chain. Sometimes you got to be careful because look here, 1, 2, 3, 4, 5, 6, 7. If I went in a straight line, 1, 2, 3, 4, 5, 6, 7, it is the same in either direction. So longest chain is 7. Most substituted is actually the one I have highlighted. 1, 2, 3, 4, 5, 6, 7, because that has a methyl substituent, an ethyl substituent, and a bromine substituent. It has 3 substituents rather than just 2 if I took the straight chain that is more obvious. So this has 1, 2, 3, 4, 5, 6, 7. It's an N-heptane. And numbering wise, I would go from down here, 1, 2, 3, 4, so that I have substituents 2, 3, and 4, rather than 4, 5, and 6. So 5 and 6 are over here. And so we have 2-methyl, 3-ethyl, I'm going to run out of room, 4, and we would call it bromo. So for the halogens, fluorine, chlorine, bromine, and iodine, we call them fluoro, bromo, chloro, iodo. There is a rule that says you want to put these alphabetical, so technically it might be more correct. And we'll finish on this. To say 4-bromo, 3-ethyl, 2-methyl, and heptane. I would give credit for either of these. There's an enormous number of rules of nomenclature. The alphabetical one's the least of our worries. There's no ambiguity with them in the wrong alphabetical order, as long as you have them numbered correctly. So we'll stop there. A little bit longer video this time. And video 3 will talk more about structure and bonding and nomenclature.